Next, that is paper. Next, we are going to good morning, students. Today, our topic is paper 6, unit 14. Paper 6, unit 14. That is some applications of some important strategies in organic synthesis. Application of some important strategies in organic synthesis. So first, we are going here 3, 4, 5 important strategies are there. One is chemoselectivity, regioselectivity, stereoselectivity, cyclization reactions, and reversal of polarity. First, we are going to chemoselectivity. First, we are going to discussing chemoselectivity. Chemoselectivity. First, we are going to discuss chemoselectivity. So, chemoselectivity means any chemical reaction, any chemical reagent, any chemical reaction, the attacking reagent preferentially react with one function group by leaving other competitive function group is called chemoselectivity. Okay, chemoselectivity means, so in a chemical reactions, if attacking reagent preferentially react with one function group by leaving other competitive function group, that is concept important. By leaving other competitive function group is called chemoselectivity. Okay, that is called chemoselectivity. I'm given a best example here. I'm giving you here. We are going to discussing ester. Okay, ketone and ester is there. Ketone and ester is there. When this compound, ketone and ester is there. When we taken, when we discussing here, keto and keto and ester is there. Here two function groups are there. Here two function groups are there. When this compound reacting with red aluminum, when this reacting with red aluminum is a reagent, red aluminum. So here two function groups are there. So this red aluminum preferentially react with ketones. So by leaving other competitive function group is ester. Okay, so this is converted into alcohols by leaving other competitive function group. Ester is leaving takes place. Therefore, this is chemoselectivity. Okay, so that in a chemical reactions, reagent preferentially react with one function group by leaving other competitive function group is called chemoselectivity. This is a chemoselectivity. So we are going to, this is when this compound, okay. So example in your notes where I'm discussing here, alcohol. When this compound undergo oxidation, so oxidation transform, that oxide converted into keto. That hydroxy group is converted into keto. Okay, so the synthesis of this target molecule, from the starting material is when this compound reacting with red aluminum, the product is alcohol. So this is the first example. And second example, para-acetyl aminophenol. Next example is para-acetyl aminophenol. So when it is undergo function group interconversion, so now acetyl is converted into amine. Okay, now synthesis of this target molecule. Para-aminophenol. When this para-aminophenol reacting with acetyl chloride in presence of base, here acylation is possible on amine and hydroxy group is there, but this is a more electronegative atom. This is a less electronegative atom. Therefore, acylation preferentially takes place on amine. Okay, so this is a best example, chemoselectivity. So the attacking reagent preferential reacting with one function group by leaving other competitive function group is called chemoselectivity. Acylation mainly takes place on nitrogen of amine. Okay, this is para acyl aminophenol is the product synthesis. Next one is third example. Third example. The third example. In this case, we are discussing benzyl oxycarbonyl chloride. This is benzyl oxycarbonyl chloride. Benzyl oxycarbonyl chloride. When this benzyl oxycarbonyl chloride undergo function group interconversion, now ester is converted into acid chloride. This carbonyl chloride is the product. This is called phosgene. This is phosgene. Now synthesis of this target molecule. Synthesis of this target molecule from benzyl alcohol plus phosgene. Benzyl alcohol phosgene in presence of base. Loss of HCl. Benzyl oxycarbonyl chloride is a product. Benzyl oxycarbonyl chloride is a product. Benzyl oxycarbonyl chloride is a product. Next, fourth example. Fourth example. This is a fourth example. In this case, now this target molecule, and this target molecule is protection of ketones as acetals, and hydroxy group is converted into ester. So now synthesis of this target molecule is that when keto ester, when reacting with glycol in presence of acid medium, this keto is protected as ketol. Keto is protected as ketol. When this compound is reduction with lithium aluminum hydride, already we know that lithium aluminum hydride, ester is converted into alcohols. Ester is converted to alcohol, and now it is hydrolysis. Now ketol is converted to ketone. And this target molecule will be synthesized. The target molecule will be synthesized. Okay. Next, fifth example. Fifth example. One, two, three. 3-ethoxy 1-propanol. 3-ethoxy 1-propanol. 3-ethoxy 1-propanol. When it is undergo functional group interconversion, ether is converted to alcohol. Ether is converted to alcohol. This is a target molecule. Okay. Then synthesis of this target molecule from this 1,3-dihydroxypropane. That is when 1,3-dihydroxypropane reacting with sodium hydrate. So here two are the identical. Therefore, reacting with 1 mole of sodium hydrate, any one of the hydroxy group undergo reacting with sodium hydrate, then forms in O minus Na plus. Now it is reacting with ethyl bromide. Loss of NaBr. So the product will be the O minus ethyl plus, and that product will be same. That is obtained that sub-target molecule. Next one is sixth example. Sixth example is that is analysis of 3,4-chloro-3-methyl-benzoyl propanoic acid. Chloromethyl this is a target molecule. In this target molecule, undergo function group interconversion, then convert into chlorotoluene, orthochlorotoluene. Orthochlorotoluene is the product. Orthochlorotoluene is the product. Orthochlorotoluene is the product. Now, synthesis of this this target molecule from orthochlorotoluene is synthesis of the target molecule from orthochlorotoluene is when reacting with malic anhydride, when this compound react with malic anhydride in presence of AlCl3, acylation takes place. Friedel-Crafts acylation is the product. Friedel-Crafts acylation is the product. Okay. This is a chemoselectivity. What is a chemoselectivity? That in a chemical reaction, the attacking reagent potentially reacting with one function group by leaving other competitive function group is called chemoselectivity. Next, we are going to regioselectivity. Regioselectivity. In a chemical reaction which produces unequal amount of structural isomers, unequal amount of structural isomers are the products, then that is called regioselectivity. Any chemical reaction produces unequal amount of structural isomer is called regioselectivity. Okay, we are going to discussing some examples regarding to the regioselectivity with respect to symmetric, with respect to synthetic strategies. So when this is a target molecule, that is 3-benzyl 2-cyclohexanone, 3-benzyl 1, 2, 3, 3-benzyl 2-cyclohexanone. Cyclohexanone is the product. When this target molecule undergo function group conversion, if the bond will be cleaved, then forms cyclohexanone is 2-cyclohexanone is the product. In this 2-cyclohexanone plus this is a benzyl bromide, and these 2-cyclohexanone undergo again function group interconversion. The bond breakage like takes place here like this, plus halo 1, 2, 3. This is a product. Okay. Now we are going to synthesis of this target molecule, that is 3-benzyl 2-cyclohexanone is the target molecule synthesized from these two starting materials. So we are going to synthesize this target molecule from these two starting materials. First, it is reacting with base. Base subtract the proton from here, and proton is subtracted by the base, then produces a negative charge at alpha position of the carbonyl and ester. This negative charge, when reacting with propyl halide, it is displays the halogen and ketone 3 and ester. It will be them when it is reacting with hydrolysis. base hydrolysis, elimination of carbon dioxide and elimination of carbon dioxide. Then 2-cyclohexanone is a product. When this 2-cyclohexanone reacting with benzyl bromide in presence of base subtract the proton from here, then produces a negative charge adjacent to the carbonyl. This carbonyl reacting with the benzyl bromide, then the product is 2-benzyl 2-hexanone 2-benzyl hexane 2-one. Hexane 2-one is the product. Okay. So next, aromatic substitutions. When this we are going to discussing with reduced selectivity on aromatic compounds. Aromatic compounds. When we take metanitroaniline, when this metanitroaniline undergo function group Twitter conversion, aniline is converted into nitro. Aniline is converted to nitro. Again, it is undergo function group elimination. One nitro is eliminated and gives nitrobenzene. Okay, function group interconversion. Orthonitro, metanitro aniline. This metanitroaniline undergo amine is converted to nitro, and then product 1,3-dinitro. So there is, sorry, some distance. So metanitroaniline, this metanitroaniline, when undergo functional group beta conversion, that amine converted to nitro, that is 1,3-dinitrobenzene. 1,3-dinitrobenzene. This 1,3-nitrobenzene, one function group elimination. One nitro is elimination, they use nitrobenzene. Nitrobenzene is the product. Okay. Now we are going to synthesis of our target molecule is metanitroaniline from nitrobenzene. When this nitrobenzene reacting with the HNO3 and H2SO4. HNO3 and H2SO4. Nitration takes place at meta position to that already existing nitro group. When this compound undergo reduction with Na2S, one of the nitro is converted into amine. This is a target synthesis of target molecule, that is metanitroaniline. Next one synthesis of next example is, that is hydroxy group. Okay, there is 1,2-dimethyl propane, 1,2-dimethyl propanol, propane 1-all propanol. Okay, when this 1,2-dimethyl propanol, when it is involves undergo elimination of water molecule and dehydrotransformation, then gives alkene. When the synthesis of this target molecule is is from that alkene, and it is reacting with hydrolysis, that hydroxylation takes place at second with carbon. Third example, and third example. The third example is in this compound. This is a target molecule synthesized when this compound is undergo transformation by using OH. Okay, this is target molecule. This target molecule undergo converted to epoxide. So how it is formation of this compound means opening of epoxide is when we take an epoxides reacting with methyl magnesium bromide. So attacking it less substitute olefinic epoxide carbon. This is a product. Okay, this is a target molecule synthesized from epoxides. Next, stereoselectivity. Stereoselectivity, any chemical reaction which produces unequal amount of stereoisomers. Unequal amount of stereoisomers. Any chemical reaction which produces unequal amount of stereoisomers, then that reaction is called stereoselectivity. Okay. Now, since we are going to discussing examples for stereoselectivity, is we are going to discussing with any example. Here I am taking this example for discussing of stereoselectivity, OAC and methyl. Okay, when this compound undergo functional beta conversion, then produces OAC and methyl. Okay, synthesis of this compound. Now, this target molecule, this is a trans compound and converted to cis compound, and synthesis of trans compound from cis compound is when reacting with the base, one double bond will be formation takes place, elimination of acetic acid. When this double bond reacting with acetic acid, another again acetic acid, so that acylation takes place, estoxy takes place from alpha side, because it's a beta side is a more crowding is takes place, therefore attacking from alpha side, reverse side attacking takes place. This is an example for stereoselectivity. What is stereoselectivity? Any chemical reaction which produces an equal amount of stereoisomers, that is stereoselectivity. Next one is cyclization. Cyclization. Cyclization, formation of ring from acyclic molecule is called cyclization. Formation of ring from acyclic molecule is called cyclization. Cyclization is affected by two factors. One is thermodynamical factor and kinetical factor. Okay, cyclization affected by thermodynamical factor and kinetical factors. Cyclization affected by thermodynamical factor and kinetical factor. So we are going we are going one important thing, size of ring formation. The ring formation affected by two factors. One is kinetical factor. Another one is thermodynamical factor. Kinetical factor and thermodynamical factor. Three-membered ring is highly favored in kinetical and thermodynamical factors. Four-membered ring is highly disfavored in both kinetical and thermodynamical factor. And 5, 6, 7, 8, and etc. all are favored in all thermodynamic and kinetic factors. Okay. Three-membered reaction is favored in the kinetical factor and thermodynamic factor. Four-membered ring is highly disfavored in both thermodynamic and kinetical factor. And 5, 6, 7, 8 both and etc. cyclations are favored in kinetical and thermodynamic effect. Okay, why the first four-membered ring is formation is disfavored in kinetical thermodynamical reaction means in this four-membered ring formation, in the four-membered ring formation, in the four-membered ring formation, in the four-membered ring formation, see here, the attacking groups, these two attacking groups here attacking, then forms a four-membered ring here. The attacking groups are anti to each other. Anti to each other. In generally, the attacking groups are anti to each other in the four-membered ring formation. Therefore, this is the highly disfavored in both kinetical and thermodynamical factor. Okay, the attacking groups. These are the attacking groups are anti to each other. The attacking groups are anti to each other. Therefore, four-membered ring formation is highly disfavored in thermodynamical and kinetical factor. Okay, kinetical and thermodynamical factor. So we are discussing one by one. So ring formations. So example for three-membered ring formation. Okay, three-membered ring formation. Three-membered ring formation. First example, epoxide. Best example for three-membered ring is epoxide. This epoxide obtained from alkenes. These alkenes, when reacting with metachloroperbenzoic acid, epoxides are converted into alkenes are converted to epoxides. Next one is four-membered ring formation. Four-membered ring formation. Here in this case, I am taking one example. Four-membered ring formation. This is a four-membered ring. It is undergo bond cleavages. Bromine, bromine, and ester. And RNH2. Now, synthesis of this target molecule is when reacting with alkyl amine. First, by loss of HBr. So then amination takes place. Now another HBr will be lost. The product is R methyl. This is a target molecule. Okay. Next four-membered ring example, second example for the four-membered ring. OH, OTS. OH and OTS. Okay, when this compound, this target molecule is from alpha tosyl hydroxy group, OTS, when reacting with the base, loss of tosyl, then loss of tosyl sulfonic acid. Then forms a product like this. Okay. Next, five-membered ring formation. Formation like this. Next, we go into five-membered ring formation. We are going to five-membered ring formation from gamma hydroxy carboxylic acids. From gamma hydroxy carboxylic acid, alpha, beta, gamma hydroxy carboxylic acid. When this gamma hydroxy carboxylic acid, in presence of acid condition, they produces ester is the product. Ester is the product. Ester is the product. So next one is second example is when this compound first dihydrothiofuran in bonds are breaking takes place, then XR formation, and these are again converted into hydroxy groups. Now synthesis of this compound. In reacting with SOX2, X, and it is reacting with H2S by loss of HX, 2 moles of HX, then forms our target molecule. Next one is 6-member ring formation. Six-member ring formation. Lactone. This is a lactone. With lactone undergo bond cleavage, then forms OH, OR. Okay. Now synthesis of this lactone from ester acid. It is involves loss of ethanol, alcohol, then forms lactone. Okay, this is example for lactone, and some 2 examples are there, 2-3 examples are there in your notes. We are going to discuss that examples. When we take this example, ketoamine. It is undergo function group interconversion, diketone and NH2. Okay, this is a compound, and this NH2. Okay, now this NH2 is obtained from cyano compounds. NH2 obtained from cyano compound. So this target molecule synthesis from that keto-cyano compound. When this keto-cyano compound reacting with nickel H2, cyano is converted into amine. Cyano is converted to amine. Here now, that ketone undergo ketone tautomerism, then forms alcohol, NH2. Now it is in presence of acid medium, loss of water molecule. This is a target molecule was synthesized. Next one. And second example is naphthone. This is naphthone. This naphthone. So now we are going to transform synthesis of this target molecule is when it is undergo function group interconversion. When it is undergo function group interconversion, the bond will be broken here. Then the product is OH. So now synthesis of this target molecule is acid. When it is reacting with SOCl2, hydroxy replaced by chloro, and in presence of AlCl3, Priddle-Craft acylation, intramolecular Priddle-Craft acylation, then the product is our target molecule. These are the examples for the synthesis of 6-membered ring. And when we are going to synthesis of 7-membered ring, next one is 7-membered ring. Synthesis of 7-membered ring is that benzene diazopine. Benzene diazopine is the product. This is the benzene diazopine. This is benzene diazopine. In this benzene diazopine, undergo function group interconversion, the bonds are broken here to chlorine, NHCH3, here phenyl, NH, and the product is chloroacetyl chloride. Chloroacetyl chloride is a byproduct. This is a chloroacetyl chloride. And now it is again undergo function group interconversion. Amines convert into amines. So now synthesis of this target molecule is ammonia. So loss of water molecule, carbonyl compounds convert to imine. Carbonyl compound is converted to imine. This is when reacting with chloroacetyl chloride. So elimination of 2 moles of HCl's. Then produces our target molecule. This is target molecule synthesized. Next, reversal of polarity. Last topic is reversal of polarity. Last topic is reversal of polarity. This is a very, very important reversal of polarity. So reversal of polarity. Majority of the compounds, carbon is linked with heteroatoms like oxygen, sulfur, nitrogen, fluorine, chlorine, etc. Due to electronic effects of the high electronegativity atoms on carbon skeleton, charges can be shown alternatively with the positive negative sign. This is called latent polarity. Okay, simply I'm telling you, majority of the organic compounds with heteroatoms like oxygen, sulfur, halogen, nitrogen, etc. is there. Due to the presence of this heteroatom on carbon skeleton, these heteroatoms having more electronegativity, due to the more electronegative atoms are present on carbon skeleton, that positive negative charges are separately, alternatively takes place on carbon skeleton. Okay, here I am taking this carbon skeleton. With this carbon skeleton, this carbon attached to heteroatom oxygen. Due to the more electronegativity of oxygen, this is bearing partially negative charge. Then this carbon is partially positive, alternative negative, alternative positive, alternative negative. This is again negative, like this. This is latent polarity. Okay, if we are familiar in identifying this latent polarity in a molecule, it helpful to disconnect the bonds. Consequently, it will also help to identify the correct synthons. Okay, it means identify the synthons. Okay, just I am here. I am breaking this. If I am break this bond, if I am break this bond imaginarily, so here this carbon with positive charge. Okay, therefore I am writing positive. If this carbon is negative. Okay, these are synthons. Synthetic equivalent for this here, for positive we are attached negative chlorine atom, for negative I am attached positive proton atom, like this. Okay, so for synthesis you are taken, otherwise you need to then forms magnesium halide. Okay, synthesis of this target molecule from when acetyl chloride reacting with negative and magnesium halide, it is replace the chloride ion, then forms this is a target molecule. This is a reverse law polarity. Okay, this is a very important reverse law polarity. So if we are familiar to identify the reverse law polarity, it will easy to identify the disconnection of the bonds. Okay, so next example we are going to discussing. Now this is a molecule. When this molecule undergo functional group interconversion, this target molecule we undergo functional group interconversion. The bond will be breaking takes place, and it is also undergo functional group interconversion. Here, bromine, where it is undergo functional group interconversion. Now, synthesis of this target molecule is from strophenone derivative. Bromination on methyl group of strophenone. In this compound reacting with this is the product. Target molecule be synthesized. Okay. Next ones. So 1,3-diethanes, 1,3-diethanes. We are going to 1,3-diethanes. This is a very important aldehyde when reacting with 1,3-diethane. This is 1,3-diethane. This 1,3-diethane in presence of acid medium involves in loss of water molecule. So now it is in presence of phenyl lithium and N-butyl lithium, phenyl lithium, and THF is a solvent. Abstract the proton from here. here negative charge. Okay, see here, all of you. So this is, we know already, latent polarity. This is negative charge. This is positive charge. This carbonyl carbon getting partially positive charge. When this compound reacting with diethane followed by reacting with base, this carbon getting negative charge. If the same carbon atom, the charges is reverse. If the same carbon atom, the charges will be reverse. This is called reversal of polarity. This is called reversal of polarity. Okay. So when this compound reacting with another alkyl chloride, so replace this chlorine R dash. When it is undergo hydrolysis, they produces ketone is the product. Another method is aldehyde is converted to ketone. This aldehyde is converted to ketone. This is the reversal of polarity. Okay. Whatever today we are discussing, one is chemoselectivity and regioselectivity, stereoselectivity. Fourth one is cyclization. Fifth one is reversal of polarity. So among these five, one is compulsory in your paper. These five are very, very important. Okay, chemoselectivity, regioselectivity, stereoselectivity, cyclization, and reversal. These five are very, very important. That means this 14th unit is very, very important for your exam point of view. Okay, I think everybody understood this today topic. Okay, next class we are going to another topic. Thank you. Again.